Well, I think we can probably get started. It's a little after 10 o'clock. Good morning, everybody. Welcome to the third in our series on Oppenheimer. We're kind of trying to key off of, come on in, grab some Halloween candy on the way in too, if you like. Um, third in our series, keying off of the Oppenheimer film. We had Lee last week. I didn't get to see that talk, so Lee, feel free to jump in at any point with commentary along the way. So I'm going to talk a little bit, skimming the surface of the history of astrophysics research that was associated both with the people that worked at the Manhattan Project and the H-bomb project afterwards, and the research that I grew out of the Manhattan Project. So it'll be a little bit of both. I will fully admit that this is a huge, huge topic of which I know just a tiny little bit of the pieces of. So this is not by any means meant to be an exhaustive look at it, just really a few highlights along the way. And I'm going to kind of split it up into some of the key people at the beginning of the project, what they did in astrophysics before getting into the Manhattan Project, and some of what they did after the Manhattan Project, and why you would pick these people to work on the Manhattan Project. And then I'm going to end with a discussion about a couple of the people that started out working in atomic bomb and hydrogen bomb research that then went on to really important astrophysical research, which was kind of a direct outgrowth of their research into atomic bombs. And again, this is only going to be a few highlights. There's been hundreds of people over the years that have worked on these projects, and I'm going to talk about maybe half a dozen of these, so that's not really going to be a great representation of everything. Also, for the most part, I'm not going to talk too much about their thoughts about the issues surrounding their research in the atomic, the morality of the project and whatnot. That's a very complex discussion with these people having a very wide variety of viewpoints about why they did this research and how they got into this research. And those viewpoints certainly changed over the 60 years that a lot of these people had with it. And again, that's not really so much my area of expertise. So again, just so kind of keeping this in mind, this is a tiny bit of the history of about a half dozen people out of the hundreds that have worked on it over the years. And I'll try to throw in some anecdotes where I can. There we go. So why astrophysics? Why was astrophysics important to that? And really the answer is that the first controlled nuclear reactions in the universe occurred 13.5 billion years ago, fusion reactions. And so understanding those, that was your laboratory in the 30s and earlier, that where you could actually see nuclear processes was in the universe, not so much in the lab. It was just really beginning in the lab. So, we have this experiment of the universe going back 13.5 billion years where we can see nuclear reactions, but the first controlled nuclear fission reaction wasn't really done in a laboratory until 1942. So the universe had a 13.5 billion year head start, and you really had 20 years of solid astrophysical research before that in the nuclear era, where you could actually look for evidence of the nuclear physics that you were trying to understand. Now, there were things like, particle accelerators, laboratory work, but it was very young, very new, and very difficult to do in a controlled fashion. So it really wasn't until after the war, for the most part, that nuclear experiment really took off the ground as a way of research. So anyone who was doing kind of cutting edge nuclear physics science, to some extent, had to look to astrophysics. And the areas that they were looking at were like stellar structure. What makes stars shine? And we know that's from fusion. The early work on that was George Gamow. He was part of Los Alamos and the hydrogen bomb research. Hans Bethe, we're going to talk a little bit about him. He was part of the Manhattan Project and won a Nobel Prize for essentially his work on nuclear reactions in stars. We're going to talk about Woody Fowler, who was also part of the Manhattan Project, and maybe a little bit surprising what he did for them, given the fact that he won a Nobel Prize in 1983 for nuclear physics research and its applications to astrophysics. Along with that, Fred Hoyle, not part of the Manhattan Project. But understanding stellar structure, that's where you look to understand nuclear physics to begin with. Stellar endpoints, how did stars end their lives? That was a big part of nuclear research, and that was another avenue for trying to understand nuclear physics, was looking at the endpoints of stars. Chandrasekhar, who won the Nobel Prize the same year as Woody Fowler, also for stellar research. Lev Landau in Russia was a big part of that story, and of course Oppenheimer was considering early work on the formation of essentially black holes, although his motivation for that was not really strictly black holes, because we didn't know about them at that point. It wasn't until the 60s that the first astrophysical black hole was discovered. Another area we'll talk a little bit about is Big Bang nucleosynthesis. Where did the initial elements come from in the universe? That was actually something that George Gamow started on, but it wasn't until the 1960s with Woody Fowler, Fred Hoyle, and Bob Wagner, who was my PhD thesis advisor at Stanford. That was his first project as a postdoc, 1967. I was 2 years old at the time when he was working with Woody Fowler doing Big Bang nucleosynthesis. We'll talk a little bit about that. So, I mean, that's why astrophysics, because that was the laboratory that you had before you got on to really being able to do this in the laboratory. It was starting in the 30s. Woody Fowler had a lab at Caltech where he was measuring nuclear reaction rates and nuclear cross-sections, but again, astrophysics was the place to look to test out some of your ideas. And really the first area where people considered this was stellar structure. How big and massive is a star? How bright is it going to be? And the basic concept, we're not going to throw a lot of math up here. The basic physics of a neutron star, of a star, is pretty straightforward. You have gravity trying to pull it in, and the gravity is being balanced by an outward push of pressure. So that's the first equation on the left there. The gradient in the pressure has to balance the mass that you're putting onto the star. And so basically you're adding up a change in pressure as you're integrating from the center of the star to the surface of the star, and the outward push of the pressure by having a pressure gradient has to be equal to the inward pull of gravity of the matter you're putting on top. And that's all that the first equation is saying. And then the total mass of the star has to change as a function of radius by how much you're putting on to each successive layer of the star. And that's what the second equation there is, just how is the mass changing as a function of radius as we're putting more and more mass on top. And those two things have to be in balance with each other, and they have to be tied together by an equation of state. What is the pressure as a function of density and temperature? In the early 1700s and 1800s, before we knew about nuclear physics, you could actually really do a star by gravitational contraction. You can imagine a massive body with just mass in it slowly contracting under the force of gravity. As it's contracting, it's heating up, and then that energy is coming out. That actually was sufficient. You can actually do that calculation. That's something we make undergraduate students do in kind of first year astrophysics courses, to figure out what kind of lifetime you can get out of that. And it turns out it's actually millions of years. So prior to the advent of nuclear physics, gravitational contraction was good enough to say, okay, we can make stars that last millions of years. And this is actually going to be related to the Oppenheimer story a little bit. And that was fine until people started actually realizing that the Earth was probably more than a few million years old. I think it was like the late 1800s that the geology was getting good enough to, measuring stratification in rock, to realize that Now, the Earth was probably tens to hundreds of millions of years old at least, and gravitational contraction was not good enough, that you needed some other force to create energy in the system. And that was eventually, of course, the nuclear reactions. George Gamow, who was, again, part of the Manhattan, the H-bomb project in the Los Alamos, was one of the first people to the mid-30s and late 30s to consider nuclear reactions as part of the story of where the energies of stars come from. And he tried to understand this by basically proton-proton interactions. Hydrogen atoms fusing together to make helium atoms, releasing energy and powering the stars. And he was doing that work trying to understand what we call the Hertzsprung-Russell diagram. I'm going to show you an example of that in about 4 or 5 slides. The Hertzsprung-Russell diagram is basically going out and looking at stars and making a relationship between the temperature of the star that you see. You can tell that by the color of stars. So, you know, a red star is cooler than a yellow star, which is cooler than a white-blue star. And also what the luminosity of that star is. How bright is that star? So there's a relationship between the luminosity and temperature for typical average stars. That's called the Hertzsprung-Russell diagram, or HR diagram for short. And Gamow was trying to use nuclear structure to understand those relationships there and explain that. Did not do that successfully. It was really, we're going to show you a little bit later that with work of Woody Fowler, that became better known. And again, you're basically just trying to plug into those pretty simple, straightforward equations of stellar structure, which go back to Arthur Eddington describing this work to try to come up with mass versus radius and give you an idea of luminosity versus temperature. Hans Bethe, who went on to work in the Manhattan Project, was the initial part of really understanding the basic nuclear physics going on in stars, and that's what he won a Nobel Prize for. I think it was 1967 or so. Now, as far as that equation of state, you're going to hear more about that story next week. There's 2 ways you can kind of think about that. For normal everyday matter undergoing nuclear processes, the pressure is going to be a function of the density and the temperature in the star. Both are important for stellar structure. More next week's talk by Mark Alford, and a little bit in this talk. Degenerate matter, neutron stars, white dwarfs, things that have gone through their life, they're no longer burning nuclear fuel. We're relying on the quantum mechanics. Electrons don't like to be in the same place at the same time. Neutrons do not like to be in the same place at the same time. There's a pressure associated with that, which is purely quantum mechanical. In that case, the pressure is just really a function of the density. And something Mark will talk about next week is that for white dwarfs and neutron stars, for most intents and purposes, you can pretend they're 0 temperature because the temperature of the star really makes no difference to the equation of state going on. It's all really a quantum mechanical effect. And because of the quantum mechanics statistics they're obeying, it's really just pressure as a function of density. So there's 2 different kinds of regimes that people had thought about, and both were being thought about in the 1930s. Now, Hans Bethe, before he got onto the Manhattan Project, was really the first one to lay out the 2 main processes of nuclear burning in a star. And the first is putting basically hydrogen atoms together. One thing that people had already experimentally figured out in the lab at this point is that you can measure the charge to mass ratio of a hydrogen atom using mass spectroscopy. You're basically you're taking beams of hydrogen atoms passing through a magnetic field, and based upon the curvature of the magnetic field, and you can figure out the mass to charge ratio. You could do the same thing with helium atoms as well. Helium nuclei also do that. And the helium nuclei are basically 2 protons, 2 neutrons. And the hydrogen nuclei are just a single proton. So you could sum up the mass of the 4 protons and compare it to the mass of the 2 protons and 2 neutrons in helium. And they noticed that helium was, in fact, 0.7% lighter. same charge, but less mass. And basically, using energy equals mass times speed of light squared equals mc squared, you realize that if you take 4 hydrogen atoms, put them together, you actually have to lose a certain amount of energy to make a helium atom, and that's basically nuclear fusion going on. And that was experimentally known in the lab at that point in the 30s, so this was pretty quickly come upon as like, this is likely what's kind of energizing stars. And so it was Bethe who described the 2 basic processes for lower mass stars that one expects to go on. And first is what's called the PP chain. 2 hydrogen atoms come together, they release a gamma ray and a positron, and you're left with a deuterium atom plus a normal hydrogen atom, and they can then, deuterium atom, which can then combine with a hydrogen atom. Again, you release gamma rays and neutrinos along those processes. You make helium-3, 2 protons, 1 neutron. The helium-3 can combine, and you're going to release 2 hydrogen atoms and a helium-4 atom. And along that process, you then also release energy. And then on top of that, there's another cycle that Hans Bethe identified as being possibly important in the energization of stars. It's called the CNO cycle, carbon, nitrogen, and oxygen. The chain is up there. It's basically almost a catalytic reaction. Carbon-12 turns into nitrogen-13, turns into carbon-13, turns into nitrogen-14, oxygen-15 to nitrogen-15, and then back into carbon-12 with various hydrogen and helium atoms and energy released along the way in that process. And that was also an important process identified possibly for stars. Now, at this point in the 30s, they had identified the nuclear physics that was going on, but they didn't know the proper proportions, actually what was going on in stars. One of the big questions was how much carbon, nitrogen, and oxygen are in the stars. Actually, at this point, one of the thoughts that they had that the CNO cycle was one of the most important parts in a star like our sun. And actually, it turns out really it's mostly just the PP chain. And they didn't know where the CNO came from at that point. You know, how was that made? And it's going to turn out it's going to be about another 20 years before people figure out where the CNO came from. One of the things that George Gamow was working on, could you make the CNO in the early universe, when the early universe was hot and dense? And the answer is no, but we're going to talk about that story. But this was really pre-war, and Hans Bethe was one of the first people to kind of put the concept of these chains together. And because of his really important theoretical work, when the Manhattan Project was started, Hans Bethe was put in charge of one of the prominent theory groups at Los Alamos to work on the Manhattan Project, because that was a big area of his expertise. Now, again, it took a lot of decades to really understand what the relative contributions of these different processes in the sun and other stars were. One of the questions, and this was something that Oppenheimer considered, was could the more massive stars, people knew that, okay, this probably works in the sun, some combination of the proton-proton interactions and some combination of the carbon, nitrogen, oxygen chain is working in the sun, but that's probably not enough to fuel the most massive stars, those things that are 10, 20, 30 times the mass of our sun. One of the thoughts that people had is that if the core of that star is collapsing in on itself, that is potentially a way of releasing a lot of energy. And they were thinking more in the terms of the nuclear physics at that point. As the core is collapsing, it releasing a lot of neutrinos, a lot of other nuclear byproducts that could then possibly heat the outer layers of the star. So that's one of the things that Oppenheimer was thinking about at that point. Could a massive star collapsing could a massive core at the center of a star collapsing actually fuel a star? The answer is, for the most part, probably not, although there are possible examples of that out there. Another question that people had, as I mentioned, was what were the abundances of the elements and where did they come from? If the CNO cycle is happening, where did that CNO come from? So George Gamow thought about that a lot. He's considered that as part of the creation of the early universe. Turns out that that story we're going to find out in a few slides only works for the very lightest elements. The roots for producing the heavier elements that we see in the universe really that's where the experimental work post-war really was required to coming up and understanding the different reaction chains that can have, the cross sections and reaction rates to start building those models. So there was actually really several decades of experimental study that started before the war, but really got into high gear after the war. That had to happen first before one could start making reliable stellar models to predict the mass-radius relationship. And a lot of that work was done by Woody Fowler in the 30s, 40s, 50s into early 60s. Again, it was a matter of being able to do the experiments in the laboratory before you could actually really start understanding that. And that first work was published well after the war. So on the left is a famous paper, Burbage, Fowler, and Hoyle, published in 1957. This paper does not have an abstract. It has instead of an abstract, it has a table of contents, which has about like 20 lists. It is literally 100 pages long because they're going into great detail describing the nuclear chain reactions. And so on the left there is just showing kind of this arrow diagram of various nuclear interactions that you can have and the elements that you can produce along that chain. And this is basically what the 1957 paper is about, is laying out all the different interactions that were kind of understood at the time, starting with hydrogen, building up to helium, and then all the heavier elements through iron. Once you get to iron, you're no longer releasing energy as you fuse things together, but there's still possible ways of getting beyond iron with interactions that take a little bit of energy from your star rather than and then give you that. And that was included in this work too. And it took really basically 30 years to go from the initial, okay, nuclear fusion works in stars, and here's the basic building blocks that you need. We now have the experimental work to start making really accurate stellar models. So yeah, we have a question here. This work based on experimentation or theoretical concepts? It is theoretical concepts to understand what to look for in the laboratory, but this is really putting together the best theoretical understanding with 30 years worth of experiments. And absolutely, that was really the big important part of it, is Woody Fowler and other people, of course, have basically needed 30 years to measure all the reactions that are part of this change. And even, work went on after that. I was actually reading an interview. I said Woody Fowler got the Nobel Prize in '83. I read this long interview that Caltech did when he was working at Caltech. And basically his philosophy was 30s, 40s, and 50s, I'm working in the laboratory to measure this. At that point, okay, I've done 30 years of laboratory work. That's a hard game to keep doing. And now for the rest of my career, I'm going to work on the application in astrophysics. And this was really sort of like the dividing line between his 30 years of in laboratory work and then moving into, now let's start applying this to situations. And the first place that you're really applying to is laying out the structure, the reactions for the stars. And the other thing that they did, and again, this is Bob Wagner, Woody Fowler, and Fred Hoyle. In the early universe, when the universe is hot and dense, it's a nuclear reactor. And so just as we're talking about what are the possible chains of reactions going on in a star, there was a chain of reactions that you expect to be happening in the early universe. So if you start with protons and neutrons created in the Big Bang, they should be in an equilibrium with each other, undergoing reactions, and that is what's shown on the right there. The basic protons and neutrons combine to make deuterium, deuterium going to tritium, deuterium also going to helium-3, helium-3 to going to helium-4, and then there's also beryllium, boron, and lithium being made in the early universe. There is an extension of this diagram that goes off to the right to higher elements, but in the early universe, mostly what you see there are the nuclear interactions that are put together. And at this point, there was enough of an understanding of cosmology to understand what the conditions were in the early universe, and enough of an understanding of nuclear physics to basically say, okay, for the first few minutes in the universe, it was hot enough and dense enough to do the equilibrium calculations of what elements should be made, and that was the Wagner, Fowler, and Hoyle work to predict the relative abundances of the elements. And we're going to show you a plot of that. So basically, the elements could be made in anything heavier than hydrogen could be made in two ways. Hydrogen and helium and a little bit of beryllium, boron, and mostly lithium could be made in the early universe. Everything after that is made in the center of the stars. And basically, it was a combination of this 30 years of experimental work in the laboratory combined with theoretical calculations that told you what the proper abundances of those would be. And for that work is what Woody Fowler got the Nobel Prize for in 1983, the same year as Chandrasekhar. So Burbidge, Fowler, and Hoyle was used to later really explain this HR diagram. And this is not a single HR diagram. This is sort of a schematic of many different HR diagrams. Each one of those curves is a set of observations of different globular clusters throughout the galaxy and the universe, measuring their luminosity versus temperature. So the x-axis, it's what's called a color index. We're taking optical spectra in two different bands and doing a difference between the two of those. Think of it mostly as a temperature. Temperature increasing to the left on that plot, temperature going downward to the right. And the y-axis is a total luminosity. And you have this, if you have a bunch of stars born at the same time, born at different masses, massive stars are hot and bright. Low mass stars are cooler and fainter, and basically that's that white line. And as time goes on, you use up nuclear fuel, and the more massive and hotter you are, the faster you burn up the nuclear fuel, and you evolve off of this HR diagram. And all those other observations are older star clusters that have evolved off of what we call the main sequence diagram. You can use that to measure the age of the universe by looking at, try to find the oldest star clusters you can and evolve off of it, and that gives you an idea. By applying the work of Fowler and others with the theoretical modeling, and you can then come up with how old is that stellar cluster. Things that have the full sequence, very young. Things that have mostly gotten rid of the stars, very old. And so on the right side, you see a list of the age associated with the various different turnoffs of that diagram. Very young at the top if you've got the full sequence, very old as you go down towards the bottom for the turnoff. The other thing that you might notice there is that 2 million years to 2 billion years is 3/4 of the y-axis. 2 billion years to 30 billion years is the last 1/4. So measuring older stuff is much more difficult than measuring young stuff, because hot and bright goes quickly, and so that gives you a lot of information over a short time. Old and faint goes slowly, tends to be you have to go further away to find old, because there's just not that much old stuff around us. makes it a more difficult observational task to figure out how old the universe is based upon this. But it is something that is part of the story of astrophysics. Started with nuclear physicists over time who worked on the Manhattan Project. Now you can sort of do the same thing with the Big Bang nucleosynthesis. You can look at what is the relative abundance of hydrogen, helium, deuterium, helium-3, and lithium-7. The lines there are the predictions from the theoretical calculations with the nuclear physics as understood. The boxes are the observations. And you can see that the predictions only overlap with the calculations. And the x-axis there is what is the fraction of the universe that is ordinary matter, baryons. What are these things? We can go out and measure that. And it turns out that if this Big Bang nucleosynthesis is correct, and you go out and look at the universe, 75% is hydrogen, roughly 24% is helium, and especially things like the helium-3, the deuterium, and lithium are very constraining, that if the models are correct and the observations are correct, then baryons, the normal matter that makes us, is only 5% of the universe. So if the total universe is 100%, which of course which should be, but in our case, when we talk in astrophysics, when we talk about what's the expected mass of the universe, we talk about how much stuff there needs to be in the universe so that the universe is flat in terms of cosmology. Too little stuff and the universe is kind of expanding forever, and that has a certain curvature to it. Too much stuff, the universe expands, stops, and contracts on itself. There's a certain curvature of the universe expected with that. Sort of kind of coasting along in a prescribed way, the universe is perfectly flat. And as far as we can tell, that's the universe we live in. We live in a universe that's going to stay flat forever. And we're going to call that magic balance of energy and matter 100% flat. That's the best we know from measurements today, that our universe is flat. Combine that with the Big Bang nucleosynthesis, and we know that us, the baryons, the stuff that makes up us, is 5% of that total mass and energy. And that's basically coming from just basic nuclear physics applied to that. Now, back, I said, the best estimates of people did this, then you can compare the models of the universe. How fast is the universe going apart? You can run that clock backwards. You see how fast we are going today. And we kind of like figure out how big is the universe by observation, how fast is it going apart, kind of take the size divided by the speed. That gives us an age of the universe. And we can do that with the cosmology, and then we can compare that to the ages that we calculate from the nuclear physics that these folks were figuring out. And as of when I was first coming out in graduate school in the early 90s, the best estimates of stellar ages compared to the best estimates of the age of the universe was that the stars were too old. The stars were too old. So at that point, the stars were coming out to be 14, 15 billion years old, and the universe was coming out to be about 9 billion years old. So in some sense, that's a great triumph of physics. The fact that there's two numbers there that are calculated in completely different ways. So the age of the universe from the expansion is completely coming from general relativity, and it's giving you a number of 9 billion years. And on the other hand, you're looking at the ages of the stars, which is coming from hydrodynamics, classical physics, and nuclear physics, and that's coming out to 14 billion years. And those are two completely different measurements, two completely different sets of physics, and they're coming out more or less the same. So in some sense, that's great, but there's still this real tension between 14 billion years and 9 billion years. And that was then solved in the late 90s by the discovery of the acceleration of the universe. So you might remember in the late 90s, we discovered not only is the universe expanding, but it is now accelerating at the same time. And there was also at that time some tweaks to the nuclear physics in understanding the cross sections. The cross sections weren't quite precise enough, and also the observations of the old stellar clusters were not quite precise enough at that time. And so really it was a combination of improving the nuclear physics in the early 90s, and therefore improving the stellar models, and then improving the observations of the clusters. And again, kind of getting that difference between 12 billion years and 14 billion years, where you're looking at very faint things at the bottom of that HR diagram, was a difficult thing to do. And the other thing is with the acceleration of the universe. The universe we now know is accelerating at late time, so we're going a little faster as time goes on, and so we're going a little faster now than we expected. And then when you kind of run that back, if you're not thinking about the acceleration, that makes the universe look younger than you thought it was. So when you realize that the universe was accelerating and that the stellar structure needed to be improved, then the two ages came into agreement with each other, kind of the late 90s or so. Now, this is the interesting story about Fowler. So Hans Bethe did nuclear physics, and because of his great work in nuclear physics, was made the leader of the theory group. Woody Fowler, who later also got a Nobel Prize for nuclear physics, both experimental and then later theoretical work, his job had nothing to do really with the details of the bomb. His job was to work on dummy bombs, essentially, and test the aerodynamics of dummy bombs. So when they dropped the bomb from the airplane, they didn't really know exactly how well the triggering mechanism was going to work, or how far the bomb was going to, how fast it was going to fall, how far it was going to fall. So Woody Fowler's work was mostly done in California, working on testing dropping bombs. You know, they put real explosives in it, and just to figure out, if we drop it here at this height, how far is it going to go, and trying to just figuring out the targeting dynamics. So even though he was this great nuclear physicist, his work was on just the aerodynamics of the bomb drop. I don't remember exactly where it was. I'd have to go back and look. Yeah. Okay. Yeah. No, I don't think they did. It was more or less just dropping it, and he was mostly doing it from an experimental perspective, just literally taking dummy mock-ups of the bomb and dropping it from the planes, and testing the triggering mechanisms and whatnot. So I think this goes back, Lee, in your talk last week, I came up with it. You know, why did the U.S. program work better than the German program? And partly, you know, you talked about the breadth of the people involved. And this is sort of kind of like a little example of it. The interview with Woody Fowler, it's like, you know, the too long didn't read version of it was Axis bad. We needed to defeat them, and I'm not going to insist that I have to do nuclear physics. If they need me to test, you know, bomb drops, that's what I'm going to do. It's you know, this was an existential threat as far as they were concerned, and therefore anything he could do to help with that effort, even though that wasn't his necessarily real area of expertise, he was going to do it because that was that important a job. So you basically had a Nobel Prize nuclear physicist working on aerodynamics. Yeah. Yeah, my impression from reading the interviews with Fowler was that it was very uncertain, and that was really the big part of it. That so the bulk of his work was empirically testing that and really working on that aspect of the problem. So really, he had very little to do with the actual nuclear bomb part, and really mostly just that specific aspect of the program in the end. Now we'll talk a little bit about Oppenheimer's work. Now, of course, we talked about a star is fueled by nuclear reactions, but eventually that fuel is going to run out, and what's left over is going to depend on how massive that core is left over. If it's less than 1.5 solar masses, it's going to contract until the electron degeneracy pressure from quantum mechanics stops you from collapsing, and you're going to be left with a white dwarf. And that's something roughly the mass of the star and the size of the Earth. If that core is more dense than about 1.5 solar masses, the electron degeneracy pressure is not enough to stop the star from collapsing. The electrons and protons combine to create neutrons. It shrinks down smaller, and you get something that is roughly the size of St. Louis, and that's a neutron star. So the mass of the sun and roughly the size of St. Louis. And if it's more massive still, and this is something still debated, exactly how massive that needs to be, but this will be Mark Alford's talk next week. We think on the order of about a little over 2 times the mass of the sun. Even the neutron degeneracy pressure is no longer able to stop it from collapsing, and that's going to collapse to a black hole. Now, the work on this was a lot of the basic work. The understanding of white dwarfs was Chandrasekhar in the early 1930s. The transition from white dwarf to neutron star, Lev Landau in 1938, and you're going to hear this more in next week's talk, also Oppenheimer and Volkov in 1939. And then the transition from a neutron star to a black hole was Oppenheimer and Snyder in 1939. Chandrasekhar was he was University of Chicago, also Nobel Prize winning physicist for his work on white dwarfs and understanding that, won it with Woody Fowler in 1983, was invited to be part of the Manhattan Project, but never actually got there because his security clearance took too long to get going. So he would have been part of the Manhattan Project, but did not get a security clearance in time to do that. Now, for Oppenheimer and Volkov, basically, you're going to hear more about this from Mark next week. Again, it's the equations of stellar structure, but then they combine it with general relativity. And they also combined it with their best understanding of nuclear physics at the time and the degenerate matter. So they replaced the equations there with general relativity equivalence. Instead of just a simple pressure, you have from general relativity what's called this stress energy tensor on the right, and the equations get more complicated when you're close to where the matter is. It's what's called the Schwarzschild solution outside of the surface of the star, which as you get further and further away, gets closer and closer to Newtonian physics. And they used, again, this kind of equation of state where the pressure is just a function of the density. And they came to the conclusion that the maximum stable mass you could have at that time was about 7/10 the mass of the sun, with their best understanding of neutron physics at the time. That's actually not far off the truth. We think it's more on the order of 2 solar masses, and again, that's something that Mark is going to talk about next week. After that, they then went on to a paper. Oppenheimer and Volkov is complicated. At this point, it's no longer analytic solutions. You require really to do this numerically. And this conclusion that it's going to collapse if it's bigger than 7/10 the mass of the sun, they admit it that's the best we can do with our understanding of nuclear physics today. Our understanding of nuclear physics could be incomplete and therefore alter our conclusions. But it was close enough to get within a factor of 2, we think. Or if that's not true, another possibility they consider is that maybe there are no equilibrium solutions. Maybe this object is going to continue to collapse. In fact, that was actually one of their initial motivations, that this collapsing object would be a way of energizing the rest of the star and maybe a way of making very massive stars. This is a concept that we've actually come back in modern astrophysics, where you could possibly have a neutron star or a black hole at the center of the star with this big massive envelope around it falling onto that neutron star or black hole, and the gravitational energy released then energizes the outer part. That's called a Thorne-Zhitkoff object, based upon a model by Kip Thorne and one of his graduate students at the time. And we do think these objects actually do exist in the universe. So he was getting tantalizing close to a theoretical concept that was really reproposed about 30 years later, or so. It was late 60s, early 70s that the Thorne-Zhitkoff objects were considered. And one of the things that Oppenheimer and Volkoff realized in their calculations when doing this is that when this object is collapsing, if you're on the surface of that, you see yourself collapsing toward the center in real time, in a finite amount of time. But because of the strange effects of general relativity, if you're very far away from the surface, when you're looking at this object collapsing, time is running differently from your perspective. Time near the surface of that is going much slower. So to someone far away, essentially they recognize that a very far away observer is going to see that collapse take an infinite amount of time. And that was really the work of Oppenheimer and Snyder in 1939 to describe that. So they basically repeated the calculations where they said, let's pretend there's no pressure, too difficult to do that calculation. We're just going to follow the free collapse of this object. And how does it look to someone falling with the collapse? And how does it look to someone far away? And so someone falling with the surface sees themselves going to the center in a finite amount of time. But from someone viewing it very far away, essentially what they do is seeing this surface created. The inside kind of comes out, the outside kind of comes in, and that surface is contracting to this radius called the Schwarzschild radius. So the Schwarzschild radius is 2 times Newton's gravitational constant times the mass of the object divided by the speed of light squared. For one solar mass, that's 6 kilometers. So from an outside viewer's perspective, very far away, you see the whole star kind of basically shrink to this surface. And that surface becomes progressively more and more gravitationally redshifted. The photons coming from that surface get shifted to lower energy due to the gravity of the object there. That happens very rapidly. So essentially you see the whole star shrink to the Schwarzschild radius and go very dark and very low energy. And also the angles at which the light comes out for it gets beamed away from you more and more progressively. Not only is it getting redshifted, not as only going to the surface, it's also kind of all going bent to the black hole. So essentially, it's not so much that you see a black hole being formed, you see this black surface forming, and from your perspective, it takes an infinite amount of time. Although practically, it goes to the surface and gets redshifted out of your view so quickly that for all intents and purposes, it looks like a black hole. But when we talk about astrophysical black holes, we're really always talking about this surface which is receding from our ability to measure it over an infinite amount of time. But most of that disappearance happens very, very quickly. And then if we could make infinitely precise measurements into the infinite future, then we could see the small ripples that are left over of that. So Oppenheimer and Snyder derived approximate asymptotic solutions for this because the math is really too difficult. Essentially, these days, people have redone these calculations, and all modern solutions to this are numerical solutions because it's kind of too difficult. So this is a Canadian group, I believe, that did this, showing two black holes from our perspective. And again, technically, we're not seeing a hole there. We are seeing a surface, but that surface is ringing down to this classical Schwarzschild solution, which in this case, a rotating black hole, a Kerr solution, and it's getting there very quickly and asymptotically approaching what we know as the analytic solution for a Kerr black hole. And then that ringing down is what we see in gravitational radiation. And these numerical calculations are really relying on these numerical solutions. And what you see in that ringing really is this relaxation to this Kerr solution. So technically, if you would keep going along to the right there, into the infinite future, there would still be a little bit of structure to that, but it would be so small as to be really irrelevant to our ability to detect it. It took, 40 years of very hard work to see the first few tenths of a second of that, and then that infinite future part is even smaller and smaller. So the rest of the story, we'll go through a bit maybe more quickly. Theoretical physicists were looking to astrophysics. Theoretical physicists from the Manhattan Project were looking to astrophysics because that's where the real world examples existed. Complex calculations increasingly meant numerical techniques had to be employed. One of the first areas for numerical techniques, the hydrogen bomb implosion calculations, to understand whether you could really implode the hydrogen inside that, relied on, are there waves reflecting from that? What is the radiation coming out of that that's potentially cooling it down too much to be below the threshold to have the nuclear reactions happening? That had to all be done numerically to solve. At first, numerical techniques really meant human computers. There's an interesting story in Feynman's autobiography. Surely you're joking, Mr. Feynman, about long rows of tables of people doing these numerical calculations, and him going off on a trip one time and coming back and finding out that the people figured out how to do corrections of the calculation in the middle, and it's like, go away, we don't need you here to tell us how to do these calculations. But later it became computers, and it's really the hydrogen bomb work where a lot of the modern computational techniques happened. The complex hydrodynamics and the radiative nuclear physics also turned out to be in supernova calculations. So I'm going to tell you the story quickly of a few of the folks who worked on these numerical techniques that started with the hydrogen bomb. And then because the numerical techniques that they were developing for the hydrogen bomb and the physics that they were considering applied to supernova, later went on to work in astrophysics specifically. So there's this long history of some of the scientists at Los Alamos and also Livermore. I took out Los Alamos from the title of my talk because this work really happened at Los Alamos, and then with the hydrogen bomb work, started also at Livermore National Labs too, the two of them working on that. So there were some scientists that worked in both bomb world and astrophysics world at Lawrence and Livermore and Los Alamos, and the institutions themselves participating in both worlds. So the post-war examples, one of them is this astrophysicist Sterling Colgate. He started, he was around from 1925 to 2013. He began experimental work, first at Livermore, then Los Alamos, doing measurements of bomb diagnostics, trying to use gamma ray detectors, neutron detectors, high-speed film to understand the energetics and dynamics of the bombs that they were testing. That later led to him doing theoretic work on supernova explosions. He actually was at Los Alamos as a high school student. There was this Los Alamos Ranch School. Oppenheimer spoke at his high school graduation. in between high school, and actually Oppenheimer helped shut the school down because it was a bit of potentially a security issue to have a high school there. And so he went off into instead the Merchant Marine. Sterling Colgate, named Colgate because he was part of the Colgate Palmolive fortune family. He went off to the Merchant Marine. He was there out on the Pacific Ocean during the bombing of Hiroshima, at least according to his account. After the bombing, when the captain of the ship heard about the bombing, he's like, "Oh, we have this high school kid who knows all about this stuff. Hey, Sterling, can you give us a talk explaining the physics of nuclear bombs to us?" And Sterling, I think, actually being smart enough to understand what was going on, and I don't know how much of the story, so gave an impromptu lecture on the deck of the ship about how the nuclear bomb worked, as essentially as a recently graduate high school student working for the Merchant Marine. Post PhD, he worked at Livermore in Los Alamos. Again, started off with atmospheric sampling of neutron and gamma ray measurements to understand energetics of the bombs. Then in the late 50s, he was hired as a consultant by the Air Force to talk about how do we verify nuclear tests from the Russians, and he proposed a satellite system to detect hydrogen bomb tests. But at the time that he proposed that satellite system, he realized that those tests could also be used to look for supernovae. And that is actually part of the story. So one of the things, what came out of that suggestion was the set of satellites called the Vela satellites. These were not NASA satellites. They were Department of Defense and Atomic Energy Commission satellites. There were these cesium iodide crystal detectors. Gamma rays come in, interact with the crystal. You see the gamma rays being sort of essentially slowed down by the crystal. That leads to Cherenkov radiation because the speed of light is slower in the crystal. You can measure that and reconstruct the energy of the gamma ray. You could also tell the direction the gamma rays are coming from to some extent. And because you had multiple, and that said, you have gamma rays are coming from big nuclear explosions. And when they flew these satellites from 1967 to 1972, they measured a grand total of 16 very energetic gamma ray events that lasted from roughly 1/10 of a second to 30 seconds. And based upon the fact that they could figure out where it was coming from, at least well enough, they knew it was not coming from Russia. They knew it was not coming from the atmosphere of the Earth, but it was coming somewhere from far out in space. And these were gamma ray bursts. And basically, there's two kinds, and there's the ones that are the 1/10 of a second. There's ones that are longer than 1/10 of a second. We now believe that the ones that are only 1/10 of a second are two neutron stars colliding into each other, forming a black hole like you saw in that movie there, and creating gravitational radiation. And those are the short gamma ray bursts. And there are longer gamma ray bursts, which we believe are stars collapsing into supernovae, which are on the unusually bright end, and we happen to be looking at the proper angle to see a jet of material coming in our direction from those neutron stars being formed, or black holes being formed. We call those hypernovae or kilonovae. So his basic idea that, okay, yes, we could use these satellites to look for Russian bombs, but we're also going to do some astrophysics too, was essentially correct and found in the late 60s. It turns out it's a little bit of myth. The story was that, okay, all this was classified and didn't tell anybody until the Defense Department said you could. The data was not actually classified. People could have found it in the data, but this is really pre-internet days, so getting data and running through it and really analyzing it was not such an easy thing to do in the late 60s, early 70s, without actually having a good connection to someone sending you the data on a physical tape or the like, and having a computer system that could read through it. Today, it's much easier. Everything goes on the internet. And so any data that NASA does becomes public anywhere from 1 week to 1 year later, and anyone can analyze the data. The only reason why this really took 4 or 5 years to come out is because it was Defense Department, and unless someone knew to ask for the data, they weren't going to see it at all. So, yeah. They saw, it was a 5-year time frame, and they saw 16. Yeah, so we later made a satellite that the first satellites went specifically looking for that. We see about one a day with the modern satellites. It turns out that how many, and it's probably on the order of that, we're seeing a fair fraction of them. So it's a few times a day. But it turns out that if you go through the calculations, how many supernovae happen in the observable universe, it's about 1 a second. So somewhere in the observable universe, if you knew where to look, there's a supernova happening every second. So about 100,000 a day. But we need like 2 or 3 of these to be unusually bright enough and beam towards us to be seen as gamma ray bursts. So these are like kind of 1 out of 100,000 events. And some combination of how bright are they intrinsically and how lucky we are to be along the direction where most of their energy is coming out. Yeah.
How many during that period of time they had satellites up? How many actual nuclear tests they?
I think the answer is from atmospheric nuclear tests. I don't think they observed any. I don't know if they observed any on the ground. That's a good question. I honestly don't know how many the satellite actually detected. So after that experimental work, Sterling Colgate and his collaborators then went on to more theoretical calculations of supernova explosions. And the concept that he first came up with was this idea of bounce back, that if I have a surface of a star collapsing to a neutron star, the outer layers of that star could bounce off the surface and come flying out at high velocity. And the concept of this, and this is something, again, with the simple calculation we give to our undergraduate physics majors in mechanics. If you imagine dropping 2 balls towards the floor, you have one heavy ball and one lighter ball, and they're coming down together. The heavy ball hits with a velocity dependent upon how high you dropped it from. That velocity is going to go as the square root of the height you started from. It's going to hit the floor first and bounce back with that same velocity. Then if I look at the ball that's just coming right before it, and if I go to the frame of reference where this big ball now coming up is not moving, this ball is coming down at twice the velocity, bounces back at twice the velocity. If I now go back into the frame of reference where the floor is not moving, it's now coming up with 3 times the velocity. So this ball is now going to go to 9 times the height that you dropped it from. So this is kind of like a way of this bounce back. You have lighter and lighter layers bouncing from the heavier and heavier layers before. You can take a small fraction of the energy mechanically and fling this outer layer out very far, very fast. And this is the idea of bounce back. And in a star, you would do this with shock waves. It turns out this doesn't actually work, but this was the initial concept of that people thought for supernovae. Anytime numerical, and it was really these numerical calculations that Colgate and others did that eventually showed we could not find a way of making it work. Instead, they later in the next set of codes went on to imagine, well, not only do we have this matter coming in and potentially bouncing off the surface, but as the neutron star forms, we're going to have a period of time where we release a lot of neutrinos from the collapse of the material there, the electrons and protons combining to make neutrons. They're going to release neutrinos. Those neutrinos are going to come out and then possibly heat up that atmosphere around the star and then be able to push that atmosphere out. And this was a 1966 paper that Sterling Colgate wrote. They kind of had to put the neutrinos in by hand at this point. And they could make the explosion actually end up working in the end. And it turns out neutrinos end up being a very, very important part of explosions in supernovae. And the question is, have we ever seen this actually happen? And the answer is yes. In 1987, there was a supernova explosion in the Large Magellanic Cloud, which is a small satellite galaxy going around our galaxy. It's only 150,000 light years away. It is the closest supernova that's happened in my lifetime. There have been closer ones, but they've happened 400 years ago, or 500 years ago was the last one that happened that was visible in our sky. They should happen like once every 100 years, so we're due for one, but this was the closest one that's happened in my lifetime, 1987. And luckily, there was an experiment working in Japan, Kamiokanda, which was up and running looking for neutrinos, and they saw a grand total of 12 neutrinos associated with this supernova explosion that happened in 1987. The neutrinos actually came first. We had to go back and look. The neutrinos came about 18 hours before the light was seen from the explosion, but the light had to take a little bit of time to get out of the supernova. Likewise, the neutrinos themselves took a little bit of time to get out. You can see that these neutrinos come over a grand total of 10 or so seconds, which is much bigger than the size of the neutron star. Normally, we think of neutrinos as just being able to pass through almost anything, but this is such a dense environment that neutrinos actually scatter and take a time to kind of randomly scatter out of the supernova and get to us. So this is experimental verification that neutrinos are actually an important part of the process, supernova explosion. Now, further numerical astrophysics. The other one of the early pioneers of going from bomb calculations to astrophysical calculations was Jim Wilson, 1922 to 2007. He worked on the Manhattan Project, and then later at the Livermore H-bomb project, and then into astrophysics. I cannot actually find any description of what he did for the Manhattan Project other than all of the reports saying his role was minor. The only thing I have found, and this might be a joke, is that his first day there, someone came to him and put a piece of plutonium on his desk and said, "Here, tell me what the metallurgical properties of the plutonium are." One, this is really, seems to us a crazy, dangerous thing to do. And two, he said afterwards what he did was later in the afternoon took a hammer and smashed a few times to talk about. Not a great thing also. Luckily, not a very pure piece of plutonium. Although, unfortunately, he did die of cancer in his early 80s. I have no idea whether that's related or not. That's the only thing I can find about what his Manhattan project role was. He then got his PhD from Berkeley in 1953 and joined the Livermore group working on the bomb project. Then if you look between the 50s and 70s to try to find his papers, they basically don't exist. Mostly because they were all classified, and it was all numerical work on building numerical codes to describe the bombs. And that went on until he took a sabbatical in Cambridge in the late 60s, and there got really interested in astrophysics and applying. He had basically been developing a lot of the numerical techniques that we use in modern day for the bomb work, and then he started applying that his expertise to astrophysics problems, essentially supernova explosions and general relativity, and then he began a lifelong collaboration with Hans Bethe after that. So this is one of his first papers, LeBlanc and Wilson. It's the collapse of a rotating magnetized star. At the top is the start. The curves are on the left are the density contours. And the curves on the right are the magnetic field. You can see that it's only one quadrant because numerical work is hard. In this case, what you're doing is you're assuming that the rotation is perfectly symmetric, that you're looking at a rotational symmetry, and then the north-south directions are perfectly symmetric as well. So you only have to do a two-dimensional calculation in one quadrant. And mostly you did that because that is all you could afford to do computationally. So these days I could probably run this under Microsoft Excel on my laptop and do the equivalent calculation. Back then, this was a long time on very expensive computers. And one of the reasons why you started this in Defense Department is because they're the ones who really had the computers that can do it. And then below that is the collapse 3 seconds in, the star collapsing in the magnetic field being altered by the collapse of that star. The grid here is 40 by 40, very small grid to actually be doing this. We do much bigger ones today. And you had a non-relativistic, highly symmetric, idealized. The simulation did produce a jet. There was much debate for many decades how much of that producing of a jet coming out of the axis is an artifact by the fact that you've assumed a lot of symmetry going on. Later, a couple years later, he started adding neutrinos and general relativity and considered accretion onto a spinning black hole. And then in 1974, something that, following on the work of the previous Colgate paper I showed, he showed that neutrino deposition into the energy of the envelope could be very important for driving the outer envelope of the supernova explosion. And this is a paper by Hans Bethe and Jim Wilson from 1985, showing that the neutrinos being deposited into this outer atmosphere could be an important part of the story in driving off the supernova explosion. So I'm going to show you now, this is what it looks like, the same calculation done today. This is Adam Burrows, University of Arizona. And essentially what you see in the center there is the black hole with the jets coming out, two different views. And you can see that we've gone from this nice 40 by 40 quadrant to this big several thousand by several thousand by several thousand simulation. And we're no longer assuming symmetry in this. And this is really just both the advancement in techniques for numerics and the advancements in computers to making this all much more feasible. So this is essentially what it looks like 50 years later, going from what Sterling Colgate and Jim Wilson did with these highly idealized supernova calculations, which really started in the bomb work, to the modern calculations. So I'm going to kind of end here. So the astrophysics research really is continuing at Los Alamos and Livermore. Los Alamos has about 50 astrophysics researchers and does maintain this very strong focus on numerical astrophysics. Here is, we'll kind of click that at the bottom, a simulation that they did. This was part of the merging neutron stars that LIGO, the Laser Interferometry Gravity Observatory, saw happen 5 years ago, I think it is now. And this was kind of the simulations they did to kind of explain what was going on there. So the kind of like the moral of the story is that back in the day, people first looked to astrophysics because that's where you found the examples of these real-world nuclear physics. It took a while to do these things in the laboratory. Numerical work and simulation work was always very important to the bomb development, and that later then got translated into astrophysics research, and that's sort of that work continues to this day at these institutions. So I'll kind of stop there and take any questions. Yeah.
A couple of questions. One is, you said that the neutrinos from that one observation reached the photons. Aren't neutrinos smaller than photons?
Yes, and in fact, yeah.
Also, a second question would be, does the sun's outer material absorb all that gamma radiation being given out by the how come we aren't radiating all of our gamma radiation?
Okay, first question. It does, yes, do neutrinos have mass and therefore travel at less than the speed of light? And the answer is yes, but they're very, very low mass. And in fact, this 18-hour delay between the neutrinos and the light, and also that 10 or 20 second spread in the neutrinos. At that time, oops, let me close that down. At that time, that spread in time and the difference between the light was one of the best limits on the mass of the neutrino. And in fact, all the uncertainty as far as how could you make those limits better came down to was how well did you understand the scattering of the light to get out of the supernova, and on top of that, how well did you understand the scattering of the neutrinos? So the 18-hour difference really is the difference between the scattering of the scattering of the light, but the spread in the neutrinos is really understanding the scattering of the neutrinos. Now, normally we don't think of neutrinos as things that scatter with themselves, but they do in the case of supernova explosions. And actually something that kind of blew my mind when I saw a recent talk on neutron stars collapsing together. In the neutron star collapse, not only do you have to worry about the scattering of the neutrinos, you have to worry about stimulated emission and absorption processes in the neutrinos, and basically lasers. So in light, you can have spontaneous decay emitting light, or you can have a system where you take and you kind of pump up the energies of the atoms and you have stimulated emission. So if you beam light of the same frequency as the transition, you get these coherent processes. Happens also in neutrinos. There's almost no situation I can think of on Earth where that's relevant at all, but in a neutron star collapse, the neutrinos are, the material is so dense and the neutrino flux is so dense that you actually have to worry about stimulated emission and absorption processes of the neutrinos. That's the only situation I know of where it has to actually be put into the numerical codes. It's actually one of the harder parts of the modern numerical codes these days. Just so kind of like some of the more exotic physics in the 30s had to be astrophysics. Similarly, today, some of the more exotic things like neutrino physics has to be done astrophysics. The second part of your question, it takes a long time for it takes anything done at the center of the sun takes 1 million years to get out of the sun. So there's a lot of scattering and absorption. And in fact, you might also know that the Nobel Prize for this, we measure the neutrinos from the sun, and people found that there were too few neutrinos coming from the sun being detected in the detectors. Now, the explanation for that is because neutrinos have mass and they're changing their flavors as they come to us. One of the possible explanations, I don't think people took it too seriously, is that the sun turned off 1 million years ago, and we just haven't seen the light not get to us. So it could have been that, yeah, we understand nuclear physics, neutrinos are massless, just the sun turned off 900,000 years ago, and 100,000 years from now we're going to find out. But that's not probably the explanation, yeah.
Increases to that speed. What causes a spin that would be a quarter of the speed of light?
It's exactly that, because you're starting with something that is 3 light seconds across or bigger, going around once every month or so, and going down to something the size of St. Louis. So it's just like, you know, the.
Is there a maximum to that if you have really an incredibly large star that you could get closer to the speed of light?
It's at that point going to be down to, there's some question for Mark next week to ask about. It's going to come down to understanding the nuclear physics and will the neutron star stop itself from collapsing based upon how fast it's turning around. And that is part of the things that they're trying to measure with the gravitational radiation coming from collapsing neutron stars colliding is how fast do they get up, and what is that moment of inertia of the neutron star, and can you make, and also kind of like the the bulk properties of the viscosity in the neutron star. It's one of the observation and theoretical questions that people are trying to figure out with observations of neutron stars collapsing into each other, being made with gravitational radiation. You can sort of tease that out, and it's a lot of theoretical uncertainty, and certainly not a lot of great observations at this point. As far as we can tell, the fastest ones we know of go around once every 1,200 times a second or so, is about as fast as we've seen. If we ever find one going as fast as 1,600 times a second, that would start challenging the nuclear physics models of what you could do with a neutron star. That would put a lot of constraints on the nuclear physics if we could find something as fast as 1,600 times a second, because that should break itself apart at that point. But we haven't really found anything faster than about 1,200 times a second. Any other questions? As far as I know, Hoyle never grew to accept the idea of the Big Bang at all. He believed in a steady state universe. That was his preferred model. And Burbidge, Jeff Burbidge, also did not believe in certainly did not believe in supermassive black holes at all. And despite doing a lot of observational work that led to, along these lines, never, ever believed. And the last time I actually saw Jeff was, I gave a talk at San Diego where he was in the early 90s. I talked about galactic black holes, and so he forgave me. It's like, okay, I believe you can talk about galactic black holes. They might be real, but I'm glad you didn't mention anything about supermassive black holes, because they're definitely not real, as far as he was concerned. Well, 10 times the masses, as opposed to the things that you saw from the Event Horizon Telescope are 10 million times the mass of the sun. So he did not believe in anything bigger than 10 or 20 solar masses or so. So yeah, both Jeff Burbidge and I think Jeff would have been upset with anything bigger than 30. Yeah. So anyway, if I had talked about active galactic nuclei, the talk would have gone very differently with him there. So yes, both Burbidge and Hoyle, to their end days, were true to their initial beliefs. But that being said, I mean, Fred Hoyle's book on cosmology is fantastic, especially for non-traditional cosmologies. Was really always fantastic. He put a serious bit of stuff on like the cosmological constant back in the time when it was fashionable to say, oh, of course there's no cosmological constant. And since he was an iconoclast and looking at steady state universes, he had a lot of stuff that was outside the mainstream. And of course, the cosmological constant has come back. So there's a lot of people who knew what the implications were. He was for anything that wasn't the standard. And so in the late 60s, early 70s, the cosmological constant had kind of like, I remember seeing a lot of talks about why the cosmological constant is exactly zero, a lot of particle physics talks along those, because, theoretically you're trying to figure out what it is. So there are a lot of people trying to come up with theoretical reasons why it had to be exactly zero. As opposed to being this huge thing. And so Fred's books gave you a lot of information about the non-standard stuff that was out of favor at that time, and which has some fraction of it has come back as being very important. Any other questions? All right.